Hey everybody, hope you're having a great day. Today I'm going to be talking about the micro versus the macroscopic view of electrostatics. And we're going to sort out all the confusing terminology that goes along with those two different views. So, let's start thinking about microscopic electrostatics. Let's imagine that you're looking into space, into neutral space. And in that neutral space, this is your eye looking into space. In that neutral space, you have a positive charge and a negative charge. Well, the positive charge is going to but it has an electric field where the field lines point out, and the negative one has field lines that point in. Well, to you, these vectors are going to add and cancel each other out. So you're just going to see neutral space. Whereas in reality, there's two hidden, in quotes, point charges. Now imagine we switch on an electric field. Okay? So down here, we're switching on an electric field. And the field points in this direction. Okay? Now we're going to redraw our point charges now. Or we'll just draw them in the field, actually. Okay, so there's our positive charge. There's our negative charge. Well, positive charge wants to move in the direction the field arrows point. Negative charge wants to move in the opposite way they point. So these charges are going to reorganize themselves. So after some time, after they're done reorganizing themselves, this is what it's going to look like. The negative charge will have moved down a little bit. The positive charge will have moved up a little bit. Okay? And remember, your eye is still here. You're still looking at this from right here. Well, now you can see a positive charge above a negative charge. So let's just redraw this as if we are actually viewing from that eye right now, and we're kind of turning the paper 90 degrees, okay? What we're going to see is positive charge above a negative charge. And let's say they're separated by a distance delta x. Now this distance is going to depend on the strength of the field that we initially applied. And we can assume, for easy purposes, that there's a linear relationship between the field strength and the distance that the charges separate. So, in other words, if we apply a field that's twice as strong, the distance between our charges is just going to be twice as large. So now let's define some variables we're going to need. We're going to call this initial field we applied, this field here, we're going to call E applied, E sub apple for applied. So now, you probably know these two charges, now they're sort of separated in space, and they're going to produce, well, this forms a dipole, so they're going to produce this electric field that looks like a dipole. So it's going to look something like this. And, yep, the arrows point into the the arrows point into the negative charge. Okay. So now, we basically made this new field where there was none before. And, well, our applied field, it's still there, I just didn't draw the lines. Well, now our total field is going to be the sum of this field from this dipole and our applied field. We're going to call this field just from the dipole, ignoring our applied field. We're going to call this field E sub I for internal, like internal to these charges, or induced. And our total electric field, E tot, is going to be a sum of the induced electric field and the applied electric field. Okay, so now that we have that done, let's explain more about this electric dipole here. So we can, how can we characterize this dipole as a function of the electric field that we applied? So some molecules, if you apply an electric field of, say, like strength 1, they're going to separate a distance delta x. But other molecules, if you apply the same field, they're going to separate by 2x. Well, let's call that proportionality constant alpha, so that we have the dipole moment mu of these charges is equal to this constant of proportionality alpha times our applied electric field. So this is a microscopic view of the dipole moment. Now alpha is called the polarizability. Okay? Polarizability. This is the dipole moment. And sometimes the polarizability depends on the direction that you apply your electric field in. And in that case, this polarizability wouldn't just be a constant. It would be, well, a matrix, and then things that are bigger than matrices, you can call them tensors. Tensor is a generalized matrix or vector or whatnot. Okay, so now let us imagine a similar situation, but imagine that we start. So I'm just going to draw a circle here for a neutral point in space, and we have all these points. Okay, I'll just stop drawing them there. And let's say we apply our electric field in that same way. Well, let's say these little neutral spaces in place were actually overlapped positive and negative charges. Well, they're going to separate again, and we're going to get a lot of positive charge up here, and a lot of negative. Well, there's going to be this negative charge. So this is from the first row of balls, and then there's going to be this positive charge here from the second row, splitting into positive and negative. And all these are going to have their own little dipole field. And then what we can do is add all these together. So let's imagine that we have n little balls. We can think of them as atoms. Okay, so we have n atoms in a crystal. And imagine that crystal has a volume V, okay? And we're basically, to find the total dipole moment of our crystal, well, we just multiply by, all the little individual dipole moments, mu. And we can call that a new thing, capital P. And that's, again, going to be equal to some constant. And we're going to call that constant. So this is the constant right here. It's actually a product of two constants, epsilon naught and chi. And then we have our applied electric field. So same thing here. We're assuming this is a linear relationship, so that if we double our electric field, then we're going to double this. If we double our electric field, we double the polarization. well, this P. So this is called the polarization. And it's effectively the dipole moment times the number of those dipole moments that you have and the volume of the crystal. Sometimes you don't consider the volume. So we see that we have a microscopic property, the dipole moment, and we have a macroscopic property, the polarization. And these are analogs of each other. We also have this microscopic property alpha, which is like an atomic or molecular polarizability, and we have this macroscopic, so like polarizability type thing, which is the product of these two. Now alpha is the polarizability. Notice it's different than polarization. They look very similar, they're spelled pretty similar, but they're different. And this epsilon naught here, this is called the permittivity of free space. So the naught represents free space, and this chi here is called the susceptibility. Okay? In my opinion, these two should have been just combined into one constant, or epsilon naught here should have just been set equal to 1, so that way you just have one constant out here that would be equal to NV times alpha. I don't know why they had to make things confusing and have two constants, but we're stuck with it now, and this is how it's done. So this is called the, well, to be more precise, it's the electric susceptibility. So all these things we're talking about, there's also magnetic analogs. So there's a magnetic susceptibility, and there's a magnetic dipole, and things of that sort. So now, we just saw that our polarization P is equal to this thing. And this is basically the electric field that's due to the crystal. Now, our total electric field is still the field that's due to the applied electric field, but it's also going to be due to this polarization P, which is, in the microscopic version, we call this E sub I. Well, we're going to redefine this E applied. Just throw epsilon naught out front there and call this a different thing, just E. And we can rewrite our polarization as the right-hand side of this equation. So epsilon naught chi E applied. And we can factor E applied out, or just call it E. We can factor it out. There's a little hand waving going on here, you see. That's why, if this epsilon naught was 1, well then we could keep our definition, but it's not, and it makes things complicated. Okay, so we can factor out epsilon naught, and we can write 1 plus chi, and we can write the electric field over there. This is our total electric field now, okay? Total. So we're calling this E total, but you would hear this actually called capital D, or called the electric displacement. And it's effectively a measure of, if you apply an electric field to a material, how that material responds. It's a measure of that. So if the electric displacement is more, it basically means the charges separate more and that this constant out here is larger. Okay, so now we have a few more terms we're going to talk about here. So we said that this epsilon naught represents the permittivity of free space. Well, free space has permittivity, but so do materials. So we can call E sub m the permittivity of our material. And there's also, this is the one thing that does make sense. We can define another thing, which is the ratio of the permittivity of the material, so EM over the permittivity of free space. And this is called the relative permittivity. And this is the only thing that should have been invented. Because, you see, if epsilon naught was set equal to 1, well then these two would just be equal to each other and our life would be easier. But we're stuck with it. This is sometimes called the dielectric constant as well. And sometimes you might see it written as kappa or some other Greek letter. But we're calling it epsilon sub r. Okay, so now we have all those terms down. Now we're going to talk about one more relationship. So you know that light is composed of electric and magnetic fields, and they propagate through space at a certain speed. And that speed is c, called c, and it's about equal to 3 times 10 to the 8th meters per second. So it propagates through free space at that speed. But when light encounters a material, well, we just learned that the electric field is affected in some way, and it kind of intuitively makes sense that the light would slow down. So we're going to say the light slows down to a speed v. And there's quantity called the index of refraction, n, and it's basically a measure of how much light slows down. It's the ratio of c over v. So it's called the index of refraction. And it should always be above 1, although you can find index of refractions that are negative and below 1, and that has to do with some sort of complicated things. One of them is that a wave can have a group velocity and a phase velocity, but we won't get into that. And this n is related to the constants we've been talking about because it is the square root of epsilon r, and the magnetic analog of this relative permittivity. So we're going to call that mu sub r. And all it is the relative magnetic, well, it's called permeability when you're talking about magnetic. It's always hard to distinguish. Permittivity means electric, permeability means magnetic. But this is what it is. And you can notice you can rewrite this as the square root of the permittivity of the material, same thing with the magnetic part, over those things in free space. Okay, so we've talked about all those terms, and I hope that gives you some idea of what they mean. Now we're just going to make a table here at the end and summarize all those terms that we've talked about. We're going to make a column where we talk about the term or the quantity. We're going to say what we define the symbol as, or what you'll usually see it as. Is it micro or macroscopic? what is it a measure of, and what are the units of it. And I think units are really helpful. You can figure a lot of things out if you know the units, and because the units always have to work out and make sense. So the first quantity was the dipole moment. This was symbolized by mu, not to be confused with the magnetic permeability, but this was the separation of a measure of the separation of the charges. This was a microscopic property, and it's a measure of, I just said that, the separation of charges. And since it's separation of charges, it's got the units of charge times distance, or coulombs, times meters. And the macroscopic analog to the dipole moment is the polarization, and that's symbolized by a capital P, and it's a vector, and it's a macroscopic property. It's effectively the macroscopic dipole moment, and it's a measure of the same thing, and it has units of coulombs over meters squared. Because if you remember, when I defined it, I wrote, let's see, NV, the number of atoms or whatever you have, times the volume, times mu is equal to the polarization. So your units will work out. If you divide by volume, you effectively divide this by meters cubed, and you get that. Next, we talked about the polarizability, and that was symbolized by an alpha. Okay, and I like to do things like put little hats over things that might sometimes be tensors. So we said that sometimes it's always a tensor, but the rank of the tensor will be different depending on if your material responds to the electric field in different directions. And it's a microscopic property, and it measures the ease to which charges get separated, or ease of separating charge. As the charges are easy to separate, you're going to have a large polarizability. Hard to separate, then it's small polarizability. It's got units of volume, or meters cubed. You might say it with other units. It depends how different authors define it in different ways. And then there was the susceptibility. Notice both of these end in ability. I just noticed that. Okay, this was symbolized by chi, and I mean, it's also sometimes a tensor. And this is effectively the macroscopic version of the polarizability. Not really, though, because you have that weird other constant, epsilon naught, the permittivity free space. It's a measure of the same thing, pretty much, the ease to which charges are separated. But the units, there are no units on susceptibility. Alright, and then we have an electric field. I'll just write that down to make this table complete. It's usually denoted by E. It's both a micro and a macroscopic property, and it measures the force on a charge, or force per unit charge. So the units are force over charge, newtons per coulomb. And then there's the electric displacement, and it had the symbol D, and it was a macroscopic property, more or less, and it's a measure of, I would say, the electric field after polarization has occurred. Because before polarization, you just had an electric field, pretty much. And then, well, your electric field comes, and then you effectively generate an induced electric field. And then, The sum of both of those is the electric displacement. It's the new electric field. And it has units of coulombs per meter squared, charge per area. Same units of polarization. And then we talked about permittivity, electric permittivity. Well, I guess magnetic is called the permeability. It was denoted with epsilon. We did an epsilon naught, we also said epsilon m. But the naught's for vacuum, m is for some material. It's both a micro and a macroscopic property, and it effectively measures the damping of your electric field, or how much your electric field is cut down by. If your material has a high permittivity constant, well then it's basically not going to want to allow an electric field through it. Dielectrics have high permittivity and they do not like to have electric fields going through them. It has units of coulombs over volts times meters. Probably the hardest unit to remember is this one. Or this is the same thing as farads per meter, but I don't work with farads too much and I always forget what it means. So I try to remember coulombs for volt times meters. And then there is the dielectric constant, or the relative permittivity, and we call that epsilon sub r. It's both a micro and a macroscopic property. Well, maybe more macroscopic, or we'll say both. And it also measures basically the damping of the electric field. It should, in my opinion, is the only one that should exist. The permittivity should not exist. It doesn't have units. Okay, and then finally we said the index of refraction. It was basically a measure of how much does the speed of light slow down when it encounters material. And it's more of a macroscopic property than a microscopic, because usually when you're talking about it in physics class, you imagine a flat plane, like a plane of glass for instance, and you don't consider the bumpiness or the roughness of that plane of glass. So I would say it's more of a macroscopic property, and it measures the change in speed of light, c, or how much light slows down when it hits a material. And there's no units on the index of refraction. So that sums up the whole video right there. And I hope that makes the terms pretty clear. That's pretty much all I want to say, so thanks for watching and have a great day.